Welcome back to Codex. Our speaker today is Tim Kunisky, who's a postdoc with Dan Spielman at Yale University. Last year, he completed his PhD at the Courant under the direction of Afonso Bandera and Gerard Ben-Arous. His research frequently involves interactions between randomness, optimization, and computation. Today, he'll tell us about the positive definite approach to mutually unbiased bases. Take it away, Tim.
Good to see all of you, and for most of you to hear me. And so I'll be talking about this joint work. This is not available just yet, but in a few weeks it will be after one more layer of polish. This is together with Afonso Bandera, who is in the audience and who a lot of you probably know, and Nikolaus Doppelbauer, I don't know if he's here, but who was a master's student of Afonso's at ETH Zurich, a great student. And a lot of this comes from his master's thesis. So the mistakes are all mine and the achievements are largely Nikolaus's. So I'll be talking about finding mutually unbiased bases. Many of you are probably familiar with this problem. It's kind of a special variant of a sort of a packing problem or an equiangular lines type of problem. So here's the main definition. A set of mutually unbiased bases is a bunch of bases of complex vector space that satisfy this particular kind of complex equiangularity condition, where if you take two vectors from any two different bases, then they have a fixed magnitude of complex inner product, a fixed sort of complex angle of 1 over the square root of the dimension that we're working in. And the question that people studying these things are interested in is, for a fixed dimension, how many, what is the maximum number of these things that we can find? So I'll call this capital N of the dimension. And so I'm not an expert in these applications at all, but so they tell me when you can find lots of these mutually unbiased bases, then these systems have applications in lots of sort of quantum variants of ordinary tasks, quantum information, objects, communication, protocols, quantum codes, and so forth. But also this is a fairly natural and interesting just kind of geometric problem in complex vector space. Okay, so what do we know about these things and the numbers of them that can exist? So first of all, there is an upper bound of a flavor in its kind of usual proof that's similar to lots of things that come up in frame theory. You can derive this from the so-called Welch bounds or by some analog of the Gerzon bound for equiangular lines by basically looking at the Gram matrix of all of these bases taken together and saying something about its entries, its rank, its positive definiteness, that kind of thing. This tells you that there can be no more than d+1 mutually unbiased bases in dimension D. So that's nice. So how good is this bound? So we know a few things about lower bounds, which come from just explicit constructions of mutually unbiased bases. First of all, whenever we're in a dimension that is a prime power, then we know that this upper bound is actually correct. So we can build this number d+1 of mutually unbiased bases whenever we're in prime power dimension. If we're not in prime power dimension, we have a kind of weak tool at our disposal, which is a sort of a construction of a product of two collections of mutually unbiased bases. And the way that this pans out is that for a dimension that's a product of two numbers, we can get a number of mutually unbiased bases that's the minimum in either of the dimensions that you start with, kind of a tensor product of bases. So in general, for general dimension, what does this tell us? So let's look at our dimension D and take the prime factorization. Then the general lower bound that we get is the smallest prime power in there +1. Right, and the general upper bound we get is the entire dimension, the entire prime factorization +1. So for things that are far from prime powers, have lots of prime factors, this is a very big gap. Now, as a last remark, this lower bound is not always the best thing that we know. There are some other special constructions that sometimes beat this. For example, for a perfect square number that's not a prime power, Sometimes you can improve on this by kind of importing some combinatorial designs, Latin squares, things like this to build mutually unbiased bases in a different way. But this is about all, these inequalities are about all kind of in general. So what don't we know? The main thing that we don't know is how to figure out what exactly this number is for any d that's not a prime power. And in particular, the main, as we'll see in a second, the main sort of blockage has to do with the upper bounds. So we don't know in these cases how to improve on this d+1 upper bound, even just by a tiny amount. So we can always round down to the nearest integer, of course, and we don't know how to show that this number is at most d. In particular, even for the smallest non-prime power number, which is 6, there's an old conjecture, I guess 30 years old now, from Zauner's master's thesis, which says that the largest number, so the constructions before 6 is 2 times 3, right? So this minimum of the prime power plus 1 construction gives us 2 + 1 = 3 mutually unbiased bases. And the conjecture is that this is optimal, so that this naive lower bound is tight. But like I said, we don't know how to improve on this 6 + 1 = 7 upper bound at all in this case. So this is kind of surprising. There's lots of numerical evidence that this should be true, and yet there's this big gap theoretically. And sort of the irritating, conceptual problem is that clearly we're missing some, useful ideas on the upper bound side of this question. So, aside from just the specifics of this problem, it's just interesting to think about, for a class of problems like this, what is it that we don't understand about how to bound the largest possible number of, the largest packings in this kind of setting. So this is the question that I'll be talking about the rest of the talk. So the perspective that we'll take, as I was alluding to, is we'll think of this problem of finding large numbers of mutually unbiased species as a kind of weird variant of a packing problem. So in general, what is a packing problem? So we have some space of some vague kind, and we want to place points in it so that pairs of those points avoid certain relations, certain differences in some suitable sense between them that are not allowed. So a kind of simple and broad instance of this is finding independent sets in graphs, right? We want to find collections of vertices so that no two vertices in our independent set are connected by an edge. So here the forbidden differences are pairs that are connected by an edge. You can describe finding good codes in this way, so codes of whatever kind you like, where the forbidden differences are 2 points in the code being close within some distance. And similarly, problems like sphere packing and various relatives of this are also kind of in this family, where you can view the points in your packing as the centers of the spheres, and they're also not allowed to be at some small distance to each other. So how do mutually unbiased bases fit into this? So here the key definition is of Hadamard matrices. Again, probably lots of people have seen these. These are unitary matrices, so that all of their entries have the same norm, which is the same number 1/√d from the same magnitude, which is the same number from the definition of mutually unbiased bases. Is there a question in the chat?
No.
Oh, no, okay. I won't investigate further. So with this definition, a collection of bases forming mutually unbiased basis, or a form being mutually unbiased, is the same as if we take those bases and stick them into unitary matrices. These kind of pairwise differences in the group sense, in the unitary group of any pair of distinct ones of these, have to be Hadamard matrices, right? Because this magnitude constraint is just the same as the inner product constraint from the original definition of mutually unbiased bases. So we can rewrite this in this kind of forbidden difference way, saying that, okay, these differences don't belong to the complement of Hadamard matrices. Now, this doesn't really look like these other packing problems because the complement of the set of Hadamard matrices is not really, about matrices being sort of close together per se. But this puts, at least formally, this problem into the same kind of framework. So there was, or actually, okay, so first there's a general method for this this type of problem for trying to prove upper bounds, which is kind of a convex relaxation. So I'll talk about the connections to other maybe more familiar convex relaxations in a second, but here I'll formulate it more directly. So we'll try to prove upper bounds on how big these kinds of packings can be by building functions on our group. So let's say that we have a function that satisfies the following bunch of properties. So the first one is positive definiteness, in the sense that if I take a bunch of group elements and I make a matrix formed by taking pairwise differences in the group of these elements, and so let's say I line up, these GIs on the rows and columns, I calculate GI inverse GJ, and then I apply my function. Any matrix I get like this for any collection of group elements has to be PSD. And let's say that this function, so A here will be my set of allowed differences. It'll be like playing the role of Hadamard matrices, but more generally. And here, let's say we're working in a compact topological group or a compact Lie group or something like this, as will be the case for the unitary group in our particular case. So let's say that on this set of allowed differences, our function is non-positive, is at most 0. And the integral over the whole group, and this, when I write integrals like this, it'll be with respect to normalized Haar measure. So Haar measure normalized to be a probability measure. This is positive. This is just some kind of non-degeneracy. Then, so let's say I have a packing in my group. So I have some set so that all pairwise differences are in this allowed set A. Then we can derive a bound on how big this set can be by looking at this sum in the middle. So here I'm taking, again, think of this as a matrix indexed by the elements, by the points in my packing. So I build this matrix, this PSD matrix. I apply by taking those differences and applying F. And then I'm looking basically at 1 transpose that matrix 1, the all ones vector. So for the bound on the right-hand side, this is just coming from looking at this sum element-wise. So because F is non-positive on the pairwise differences of different G and H in my set, the contribution of kind of the entire off diagonal of this sum will be at most 0. So I can throw that away and just bound it by the contribution of the diagonal, where every F is just of the identity. So E here is the group identity. And the number of those is the size of my set. So that's where this bound on the right comes from. It comes from the blue property. The bound on the left, I'm kind of skipping a few steps, but the idea is that because of the particular kind of structure of this matrix, where a given entry only depends on this group difference, the all ones vector will be an eigenvector of this matrix, thanks to kind of the group symmetry. From a sort of representation theory point of view, this is the eigenvector corresponding to the trivial representation. And the eigenvalue will be this Haar integral of F. So the actually kind of slightly stronger version of this orange property automatically holds thanks to this group symmetry, which is that this matrix is not just PSD, but is at least the integral of F times the 1-1 transpose matrix in the in PSD Loevner ordering. So if I apply that, then here I'm taking 1 transpose times the matrix times 1. If I look at the contribution from the just this all ones vector direction, then I'll get the size of my set squared, right? The norm squared squared again of the all ones vector of that size times the integral of f over the group. So I have these inequalities on either side, and if I rearrange, I get an upper bound on the size of my packing, right? Which is f evaluated at the identity, normalized by the integral. You can also think about doing this over just f's, renormalized by dividing out the integral, and then it'll be at most the value on the identity. So this is a general method for bounding the largest size of packings with any whatever allowed set of differences you like in nice groups. Now, how does this relate to, why am I talking about this as though it's a convex relaxation of the problem of finding a packing? Well, by analogy with a few other cases, if you think about, first of all, a finite group, then this kind of problem is just finding an independent set in a graph. The sort of standard convex relaxation for this is the Lovász theta function, a semi-definite program. And in the group setting, you can do a kind of symmetry reduction related to your problem setting being invariant under conjugation by elements from your group, and then you'll get so that will take you from general PSD matrices to these kinds of matrices that only depend on pairwise differences in the group, and you'll get this kind of problem after reducing the Lovász theta function. When your group is abelian, you can view this as being kind of a version of the Delsart's linear programming method, which is kind of arose historically as a way of bounding maximum sizes of codes in, let's say, finite fields to some power. And so there, when the group is abelian, then the the sort of basis matrices to whose span, f of these pairwise differences is allowed to belong, these will be simultaneously diagonalizable. You can diagonalize, and then you can convert these semi-definite programs to linear programs. So this is from the same family as all of these other sort of packing types of bounds. Okay, so now there was a paper a few years ago. I think I noticed one of the authors in the audience that said, why don't we apply this idea to our problem of mutually unbiased spaces, even though it's a strange packing problem, even though Hadamard matrices are not kind of the usual pairwise differences we would care about, let's just try and see what happens. So in that case, what this tells us is that, let's say we have a function on the unitary group. It has that positive definiteness property. It's at most 0 on the subset of Hadamard matrices. It has this property of the integral. Then we get automatically a bound on this number n of d that we've been trying to control. So they showed this, and they also found a very interesting example where let's look at this function where I take kind of a 4 norm of my unitary matrix -1. So how will this behave on Hadamard matrices? Remember, every entry of a Hadamard matrix is 1 over root d in magnitude. So 1 over root d to the 4 is 1 over d squared. There's d squared terms in the sum. So on a Hadamard matrix, the sum will be 1, -1 is 0. So it'll satisfy that inequality constraint. You can check with a bit of work that this function is also positive definite. And you can calculate its integral using kind of standard stuff about these Haar moments of monomials in unitary matrices. And so what do you, so this is kind of a valid thing to substitute into our bound. So what do we get? On the identity matrix, right, there's only d non-zero terms in this sum. Each of them is 1, so we get d -1. The integral so happens to be d -1 over d + 1. So we simplify and we recover our d + 1 bound. So this, I didn't give the details of this Welch bound Gerzon approach to this inequality, because actually this gives a different proof that's closer to the kind of thing we're after. This gives a new proof of this d + 1 upper bound. And so, okay, this is maybe, this is nice. It's nice to know that this happens and nice to have another proof. It's a little bit disappointing, because what we were really after is improving even by a tiny amount on d + 1. But now at least we have, a plan. We have a clear idea of what we can do. We can just look for other better positive definite functions. And there are some proposals and some speculation in that paper about what kinds of polynomials might work for that. So this is the question that we'll be kind of pursuing. Is this possible? How can we decide? So like I said, we can think of this as a kind of convex relaxation of our packing problem. And from that point of view, a natural thing to do is to look at the dual program in whatever sense makes sense here. So that will give us kind of lower bounds on our upper bound on n of d, and that will control, that will say that this method can only do, so well. So let's look at how those kinds of arguments look. So these dual bounds will involve some kind of dual object to positive definite functions. And these turn out to be measures over our group that are positive definite in some suitable sense. So let's say we have a probability measure on our group. Then positive definiteness is kind of the right way to define it, is by looking at representations of our group and taking averages over our probability measure of these representations. So this is sometimes called the Fourier transform of this measure. And this gives for every finite dimensional, so in our case, the representations, the irreducible representations will all be finite dimensional. For finite dimensional representations, this gives a matrix. So you give the Fourier transform a representation and it gives back a matrix. And generally a measure is positive definite, positive semi-definite, really it should be called, if all of these matrices are always positive semi-definite. But for our purposes, let's look at a slightly kind of different variant of that condition. Let's say that we could come up with some measure, and it had this property that its Fourier transforms. So again, here it's enough to look at all irreducible representations because others will decompose as direct sums. Let's say these are all bounded below by some negative, some positive number c times the identity. So we can construct from this so here I'm doing kind of a hands-on weak duality calculation for these hypothetical dual certificates. We can construct a certain positive definite measure lambda from this mu. So what is this going to be? It'll be this number c times the delta mass at the group identity minus a multiple of the Haar measure normalized to be a probability measure plus our measure mu. So I claim that this is a positive semi-definite measure. Let's check. So we'll check by considering first separately the trivial representation and then all the non-trivial representations. On the trivial representation, right, when we average it, it's just the number 1, right? When we average it over all these measures, these are all probability measures. So we'll just get 1 everywhere. We'll get c minus c plus 1 plus 1. So that'll be the number 0. So that's fine. If we have a non-trivial representation, then on the delta mass at the identity, we'll just get the identity matrix times c. For the Haar measure term, we'll get 0. So this is kind of a manifestation of orthogonality because that integral is kind of an inner product in some sense between the trivial representation and this other non-trivial representation. You can check that you'll get 0 then. And then we can bound the term coming from mu below by minus c times the identity. So again, this will be PSD. So from a mu that's bounded below like this, we can build a PSD measure. Now, if also this has the property that its support is contained inside our allowed set of differences, then we can complete this weak duality calculation in the following way. So we'll have that if f is a positive definite function and mu is a positive definite measure, then so here you can take it on faith that these are the correct dual objects and their inner product in the sense of taking the integral of f against the measure will be non-negative. But then when we evaluate f specifically on this lambda, we'll get c times its value at the identity. Then we'll get c minus c plus 1 times its integral against the Haar measure. And then the mu term will be at most 0 because mu is supported on this set, precisely on which our constraint on F is that it is at most 0. So we have this inequality, and rearranging it, we get that the bound that F generates is at least C plus 1 over C or 1 plus 1 over C. So this is kind of a general weak duality kind of calculation saying that if we have a measure that's supported on our set of allowable differences, then we can get a lower bound on the best possible bounds from positive definite functions associated to this most negative, kind of in terms of this most negative possible eigenvalue that any of the values of the Fourier transform on irreducible representations can have. So we worked this out in general, and here is kind of the upshot for our purposes, for mutually unbiased bases. So here, remember, we're interested in our bound was 1 plus 1 over C. We're interested in whether positive definite functions can improve on the D plus 1 bound. So we really care about taking C equals 1 over D. So, and like before, we take the allowable differences to be Hadamard matrices. So we get this result that if we have a probability measure, it's supported on Hadamard matrices, and its Fourier transform in this sense, whenever we apply it to an irreducible representation, has smallest eigenvalue at least negative 1 over D. Then we would get that no positive definite function can improve on this bound, and that one example, the degree 4 polynomial, would be the best possible achievable by this method. Now, we also can get a kind of more specific version of this. So this is hard to do, as far as we know, to prove this general inequality star for all irreducible representations. But we can learn something even if we can do it for just some particular collection of irreducible representations. So every positive definite function admits an expansion, like I've written here, if we allow ourselves to sum over all irreducible representations. It can be written as this inner product of sum of a PSD matrix per representation, some linear combination of those. So the positive definite functions are kind of the cone generated by all of these things. So if we can prove this condition only for some subset of irreducible representations, then so long as we restrict a representation of our expansion of a positive definite function to just include those representations, then we'll get the same kind of result, that no positive definite function of this particular form can improve. So this will be useful because it lets us kind of really reduce this still for some interesting class of functions, but reduce this to a finite computation. If we only have finitely many irreducible representations we care about, then at least in principle, they might be very big matrices and very kind of inconvenient to compute with. But we just have a bunch of matrices whose spectrum we need to say something about, and that will give us this kind of dual bound. So just to kind of establish what we might expect to happen here, it's useful to look at another situation where people did something like this in the literature. So there's this seminal paper about sphere packing of Cohn and Elkes from a while ago that used a sort of variant of this kind of Delsart method where you can reduce these things to linear programs. And they use this to prove bounds on the largest possible density of sphere packings in Rn, or to formulate linear programs that give you bounds like this. And then a while later, they did the same thing that we're doing here and looked at dual bounds on those linear programs. And what turned out to happen is that it was hard to find these dual measures in their setting. There are also measures. And they could do this only in certain special dimensions, and only by making their lives easier by basing these constructions on modular forms, which satisfy some functional equations, some nice kind of symmetries and so forth that make them easier to compute with. And even with that, most of their results for most of the dimensions that they can handle are just numerical approximations. Whereas what we want is to say something, we want to show that the value of this dual program is exactly d+1, right? So we want these to be, and in that case, they will be kind of exactly optimal because we have this example from the primal program that achieves d+1. And we want to verify these kind of not numerically, but symbolically, right? So we expect this to be kind of hard, and we'll see that it is
Hey,
a
Tim,
little bit
can you hear me?
tricky. Yes.
Cool. I can hear you too, by the way. So is it possible, and maybe obviously so, to convert a construction of mutually unbiased bases into a dual certificate, a lower bound or the upper bound?
Yes. By taking the measure that is basically supported on just the Hadamard matrices that are pairwise differences of the corresponding unitary matrices. Does that make sense?
Great, thank you.
Yeah.
Awesome.
Yeah, so I don't think I say it. Yeah, that's it's too bad that I don't quite say it in the slides, but I'll mention where that is an important inspiration of kind of the dual certificate that we actually end up using. So right, so that's a good point. Even right, it is possible from any actual mutually unbiased basis to build a dual certificate in this way, but the trouble is exactly that we don't have large mutually unbiased bases in this dimension 6, where we're trying to show that this we think that the true number is 3, right? But we're trying to show a lower bound on this method of 7, so that can't directly help us, but looking at those things can help us try to guess what a good sort of fake non-integral dual certificate should be. Yeah, thanks for the question. Okay, so that brings us wonderfully to what our dual certificates look like. So following what Dustin said, to try to understand how we might want these things to look, we can look at cases, let's say prime power dimensions, where we do know we have these constructions of maximal collections of mutually unbiased bases, and we can look at their pairwise differences. These are Hadamard matrices, and we can look at what those Hadamard matrices are. And we notice that in some cases, they are related to this one especially natural Hadamard matrix, which is the Fourier matrix, right? This discrete Fourier transform matrix. And the way that they're related to it is that those pairwise differences are in this sense equivalent to the Fourier transform matrix. So we say that two Hadamard matrices are equivalent if you can get one from the other by this kind of transformation, where you apply. So here the diagonal matrices are really unitary diagonal matrices with unit circle complex numbers on the diagonal. So if we can get one from the other by basically phasing, on either side by these diagonal matrices, and then applying a permutation. So these operations preserve Hadamard matrices, and they're kind of simple operations. So we think of them as forming these equivalence classes. And so we make this observation in prime power dimensions. So it's not quite that they're equivalent to the Fourier matrix, but to a certain kind of tensor product of Fourier matrices. And this leads us to make a guess that we might be able to take this dual certificate measure, that is the uniform probability measure over one particular one of these equivalence classes, which is the equivalence class of this kind of tensor product of prime dimension discrete Fourier transform matrices. So what we think, kind of our most optimistic conjecture, is that taking this particular measure mu will show just overall positive definite functions that they can't improve on this d+1 bound. So this is what we hope for. We're quite far from being able to prove this, but let me show you what we can prove. And the rest of the talk will be kind of some aspects of this computer-assisted proof of this statement here. For the special case of dimension 6, this measure that I was proposing is the uniform measure over the equivalence class of F2 tensor F3, which turns out to be the same as the equivalence class of F6. I'll just call that F for the rest of the talk. And what we can show is not that this proves that no positive definite function can improve on this bound, but just that low degree polynomial ones. So in the unitary matrix and its entry-wise conjugates, that these low degree polynomial positive definite functions can't improve. So remember, the example from the Kolountzakis et al. Paper was a degree 4 polynomial. It had these norm of uij to the 4th appearing. And here we can increase this by 2 more degrees. So you can show that you only need to look at kind of balanced polynomials in the entries and their conjugates. But we can improve this we can increase this to degree 6 and show that no polynomial like that can improve on that particular degree 4 example. And so the nice thing about this degree constraint is that it lets us work in that setting I mentioned before, where we only have to look at some particular finitely many irreducible representations. And so proving this, at least in principle, is just some computation with some very big matrices and their spectra. But in fact, we can really reduce this computation quite a lot. And we think that maybe some of those reductions could help kind of give just more theoretical proofs without computer assistance. So I'll tell you about those next. Any questions about this main statement? Okay. So the main step is to observe that actually this taking our measure to be uniform over an equivalence class actually has this kind of quite natural representation theoretic interpretation. So the group of these matrices, these special unitary matrices that are permutation times diagonal, that we kind of are allowed to multiply on either side by in forming equivalence classes, is a quite natural subgroup of the unitary group. It's the permutation matrices where you're allowed to stick a phase on every entry. Sometimes people call these generalized permutations or monomial matrices, something like that. So if we look at the Fourier transform of a measure like this, then what we'll get after kind of factorizing this, the representation, we'll get that actually we're just taking the image of our Fourier matrix and then hitting it with a particular projection matrix on either side, which is the projection to the subspace of this representation that is invariant under this particular subgroup of kind of phased permutation matrices. So we might hope that this is a small subspace. And in that case, that would simplify our calculations quite a lot. And the nice thing is that this actually has a natural kind of representation theory interpretation, because, so I won't go into details at all, but if you think back to how you would classify the irreducible representations of the unitary group, there's all this talk about the maximal torus, which is exactly this subgroup of diagonal matrices, and looking at how an irreducible representation of the unitary group decomposes into further irreducible representations of that torus subgroup. And it turns out that the further action of the symmetric group of the permutation matrices on those various subspaces is also a natural thing. It has kind of analogs through these so-called Weil groups in other Lie group settings. And so, the point for our purposes is that people have studied this in the kind of algebra representation theory Lie groups literature. In particular, there's this paper from the 70s where they looked at the action of the symmetric group on the subspace that is invariant under the diagonal matrices and computed the character of this. And we don't really care about the entire character, and also didn't really compute it, but gave certain kind of, let's say, an algorithm for calculating it. But for our purposes, what this tells us is that we can calculate the dimension by just looking at the character evaluated on the identity. And what we find is that under our restriction of the degree to at most 6, that implies some restriction on the irreducible representations we have to look at. The dimension of this subspace is either 0, in which case we just don't care about it, or it's 1. And so as we'll see, this gives us a huge kind of simplification in what we have to check on the computer. So here's a table of these dimensions. So think of the number, don't worry about the middle column, is some parametrization of the irreducible representations. Think of the number on the left-hand side as being the degree of polynomials that we care about over 2. So here we're looking at 0, 1 is missing, 2 and 3, which are, the numbers up to 6 over 2. And we're writing the dimensions of these subspaces that we can reduce to on the right. And so we see for the cases that we care about, and here I'm only including the cases where they're non-zero. So first of all, there are many more irreducible representations. And in those cases, we can just ignore them completely. And for the purposes of polynomials of degree at most 6, we only have these special dimension 1 cases. For higher degree polynomials, if we wanted to try to deal with those, we would have gradually higher and higher dimensions kind of accruing here, and we would have to deal with slightly more complicated problems. So after this observation, how can we do the rest of this kind of symbolic verification? So like I said, we only need to care about those representations for which this particular dimension is 1 of this subspace. So what do? We just find a non-zero vector in there. How do we do that? We find there are some explicit bases for irreducible representations as kind of tensor subspaces. So we take those bases and we just try projecting over and over again to this subspace until we get something that's not 0. Just totally the boneheaded approach. And it turns out that this will belong to a nice, because of this kind of Young symmetrizer description of those bases, this will belong to a fairly nice tensor subspace. It'll be a span of things like this. So don't maybe worry about this for now, but just notice these are tensors. So they're in RD to the tensor power D times K, where K corresponds to this polynomial degree over 2. It's kind of the degree of both the unitary matrix entries and their conjugates. So for us, D is 6 and K is up to 3. So we might end up working in these 6 to the 18th power kind of spaces. So this is still kind of tricky, and it's fortunate that we have this dimensionality reduction, so we don't have to do too many computations with these things. In particular, when the dimension of this invariant subspace V pi is 1, then this matrix relation just boils down to a scalar relation. We can just test on this one particular non-zero vector. So we're comparing the identity, right, to something about the image of the Fourier matrix under our representation. On the identity, we'll just have the norm of our vector. So we can just calculate that. It's in this span of these kind of tensors. Lots of them will be mutually orthogonal. And there's just some counting problem in there to compute the norm. And the remaining task is to calculate this quadratic form with the image of the Fourier matrix. So I'll mention, just to conclude, what comes out of that, because there's this interesting kind of combinatorics problem that we leave as one of the curious open problems. So like I said, this vector V is in the span of these particular kind of symmetrized over the symmetric group tensors. So here the EJs are standard basis elements of RD. So it's enough, since V is some linear combination of those, to compute these kinds of quadratic forms of one of these for some particular index I with another. And what we get out of a calculation like this is a sum over permutations. So after there's some reduction you can do, you get two sums over two permutations, but it turns out that there will be lots of repeated terms. You can view this just as the second sum here over one permutation. And so sometimes you get the sign of the permutation and sometimes you don't. But otherwise, you get this, so the kind of primitive dth root of unity to the power of an inner product between these indices. So these are, remember, these are full of integers between 1 and d. I and j are there with some repetitions. And we're summing over these possible inner products between one of these and the action of a permutation on the other. So I'll talk about this a bit more in the next slide, but this is, we get this kind of formula. At least in principle, this only depends on how these indices I and j are kind of aligned. You can describe this in a graph. Again, I'll say more about this in just a second. But for our purposes, we have this, there's a relatively kind of small number of these things. So what we do for our computer verification is just upfront, before moving on with any of the main calculations, we calculate all of these, we save them, and then we kind of look them up as needed, and we finish the verification. But for further kind of theoretical purposes, trying to push this to higher polynomial degrees, higher dimensions, it seems important to understand what's going on in these kinds of sums if we hope to follow this program of using specifically the Fourier matrix. So here's an example of the kind of thing that comes up in this calculation. So here d equals 6 and that number k equals 2. So here I have numbers from, so I have 12 numbers in each I and j. D times k equals 12 numbers. The numbers are from 1 to d, from 1 to 6. Each number happens k equals 2 times. So these are some two vectors of natural numbers like that. And I can draw a bipartite graph, 6 vertices and 6 vertices, where I just record how often, which entries of I, which occurrences of a particular number in I match up with occurrences of which numbers in j. So for example, the first two entries in I are 1 and 1, the first two in j are 3 and 1. So the first vertex on the left goes to the first vertex on the right and to the third vertex on the right, and so on for all of this. So you get some regular bipartite graph like this. And associated to this, you have a sum where you think of the left as having some fixed labeling, and summing over all possible permutations that could label the right. You have this same kind of sum that we saw before, where you now take a kind of an inner product or a sum over products over edges of the two labels. And because we have this 2 pi I over d factor, we only care about this mod d. Another way to think about this is as the characteristic function. So let's say k is even, like in this case. So then the sign term goes away. This is the characteristic function of this random variable, which is this sum over edges for a random permutation sigma labeling a particular graph. So we spent a while trying to work out somehow anything we could possibly say about these quantities, but this remains pretty much completely mysterious, and it seems to be kind of an interesting open problem that would probably help push this method further. So let me just wrap up with some open questions that this leaves. So of course, the main question is to try to figure out if this construction that we conjectured will in fact work for higher degree polynomial positive definite functions, or maybe all positive definite functions, and also for non-prime power degrees other than 6. Now, towards doing that, to use this same reduction to this small invariant subspace V pi, it would be useful to understand for, at the very least, when this dimension isn't 0, what this dimension is, but really maybe more kind of carefully what this action of the symmetric group on this subspace of a representation invariant under diagonal matrices looks like. What is there some kind of combinatorially natural basis of this V pi and so forth. Then there's this summation that I showed before. So again, we really don't know what's going on with this. I mean, we actually have lots of kind of raw data about this from our calculations, but haven't been able to understand if we should expect any particular nice closed form for this kind of sum as a function of the graph, let's say, something like that. And more speculatively, maybe part of this plan is a little bit misguided. So for example, this permutation summation, the particular kind of this number theoretic stuff in there, is coming from our choice of the Fourier matrix. So maybe we can make life a little bit easier by picking a different Hadamard matrix to start with and seeing if some simpler kind of analogous problems in these scalars that come out of that are any easier to deal with. And finally, most speculatively of all, for the finite dimensional problems we talked about before, let's say for the Delsart coding theory LP bounds and for the Lowash theta function, there are natural kind of hierarchies of bounds that similar reasoning can give rise to, that can be viewed as coming from the sum of squares hierarchy of relaxations of some kind of polynomial optimization problem. And so there is a bit of literature about trying to make sense of these kinds of things in this sort of infinite dimensional setting, formulating these generalizations like that of this method of positive definite functions for this kind of problem. But even in the finite dimensional, even in the sort of finite group case, let's say this is really very poorly understood, but maybe this is a natural place to try to look for genuinely better bounds. If, let's say, our conjecture is true or some variant of it, and this method can't give us bounds better than d+1, then maybe this is a reasonable next step. All right, thanks for your attention. Happy to answer any questions.
Awesome, thanks so much.